So yes, we are recording now live. So happy New Year for everyone that is here live, and happy New Year for people in YouTube. So we are returning today for our quantum hardware course, like the quantum optics models. We stopped in the last section talking about the harmonic oscillator, and we saw how the quantum harmonic oscillator could be used like physicists in general call this like a toy model, like for a quantum computation. A toy model is something that in practice you cannot use, but the theory that we learn about this could be useful for other models. So we will see today that the things we learn about the harmonic oscillators really important for us. So I will start sharing my screen. Okay. So again, I will show some slides just to give an introduction of what we will do in this topic, and then we go to the whiteboard and make some calculations. And especially today, we will talk about a lot about some kind of states called like coherent states. That is important for quantum optics. So today we start like quantum optical models, and the sequence from after the classes, the lectures about the simple harmonic oscillator. And again, I will follow this book here, but I will use another book also when I talk about the coherent state that I will mention in when I'm talking about it. So, but the idea is follow what is in the Nielsen Schwenk book. Okay, so this is the first part. I'm thinking that talking about like the coherent state that we talk today, that's a kind of review of quantum optics. So before we start quantum computation, see this as a optical quantum computer, we will review some quantum optics tools that will be important for this. So it's just few slides, then we go to the whiteboard. So in this lecture, we will use some of the techniques that we learned previously about the quantized simple harmonic oscillator. And we will discuss a very important type of states that is called coherent states that are related quantum states that describe some kind of ideal laser light. That will be important, of course, for quantum computation. One physical system that could represent a qubit, we already discussed this in the past, could be a photon, an optical photon generated by some kind of lasers. And so just to review about photons, like they are chargeless particles that in general do not interact very strongly with each other. De facto, in the empty space, they don't interact with each other, but in some medium they could interact in general very quickly. The importance of quantum computation is related to the fact that they can be guided along distances with low loss using optical tools. Like all these tools will have some we study in details. That's why I put here in different colors. Like phase shifters and B splitters. Not be today, will be in a couple of lectures in the future. But we see some details about these optical tools. And photons exhibit a signature quantum phenomena such as the interference that produces in the double slit experiments. The people that are not familiar with this type of experiments, in the last like quantum T roundtable section, we discuss about this experiment. So I suggest some people that didn't watch it see the quantum T, the last section. We discuss about the double slit experiments. We discuss about like using electrons, but it could be also the same thing for photons. So furthermore, photons can be made to interact with each other using nonlinear optical media. So we see some type of media also in next lectures, not today. That could be we could use like in the real system to this type of media could mediate the interactions between the photons. And so the idea is in this topic now is to learn many things when studying the optical photon quantum computer components, like phase shifters and beam splitters, the architecture of this kind of computers, and the drawbacks. So, okay. So to begin today, like we consider that single photons are how they represent quantum states and the experimental components for manipulate them. So these slides here is just to give a brief summary that what we see in this topic, right? So we saw in the discussion about the single harmonic oscillator, when we quantize the single harmonic oscillator, that the energy in the electromagnetic cavity is quantized in units of h bar omega. So each such quantum is called could be called like a photon, and a cavity can contain a superposition of 0 or 1, which could be expressed as a qubit in this way. Okay. Well, this is the ground state in the oscillator, or you could call vacuum state also as well, and this is the excited state, the state with one photon, for instance. But instead doing this, we'll use a different approach. So what we in this model, what we use in this model here, we will consider two cavities whose total energy is h bar omega. And the two cavity state of the qubit could be represented by 0, 1, if the photon is present in one cavity, for instance, or 1, 0, if the photon is present in the other cavity. And the state of superposition could be given in this way. And this state we could like call the represent this state as related with the logical zero, logical qubit 0. In this state, we could choose like to be represented the one state, qubit state, the logical state. And this type of representation is sometimes called in the literature as the dual rail representation. Okay, so we will see this in the future, how we could do this, this type of model that we use to do computation. But today we need to because the idea is to, I think I have questions. No? So the idea is to understand the theory behind this. So this is just a summary. So we understand the theory, what is behind this, right? Understand the details behind all these ideas. So today we will understand what is the coherent states.
The question was from Barrand. Is this not a Bell state?
Bell state, this, yeah, is a type of Bell state, yeah. But we will associate this with the logical. This would be like the logical 0, and this is the logical 1. Okay, but I mean, this when we are doing quantum computation. So today we're not exactly do this in the today lecture. This is just a summary, it's just to give a brief idea what this topic this. But this type of model, this dual gray representation will be important. And this is in general is we'll see this in the future, but I'll give some brief idea now. In general, this is generated with phase shifters. You send like photons by a laser and goes to a crystal, and you can like generate double state, like this. It could represent like state 0, 1, or 1, 0. But yes, it's a type of Bell states. So to generate photons in the lab, so today, the lecture today is about coherent states. You understand what type of states that's so important for doing this type of computation. So to generate photons in the laboratory, we make use of lasers, and a single photon is generated by attenuating the output of a laser. And the laser output a state that is known as the coherent state that we study today. When we will represent this state by the cat alpha. Okay, it's in general we will see this in the books. We define a coherent state as a radiation emitted by a classical current distribution in such a state. This state, in the coherent state. And a coherent wave packet that is associated with the coherent state always has a minimum uncertainty and resembles the classical field as nearly as the quantum mechanics permit. So this is a type of state that is closest possible to the classical, the classical world, let's say. It's a quantum state, but it's the closest possible for the classical world. So we will see when defining that is a joint of a type of current, the current distribution that is classical associated with the potential that is quantized. So we see this today in the lecture today. Sometimes this is called like when we have this mixture with classical and quantum things. Sometimes physicists call like a semi-classical state. So the corresponding state vector, the alpha associated with the coherent state, is the end state of the positive frequency part, and we'll define this today, of the electric field operator, or equivalently, the eigenstate of the destruction operator of the field. Destruction operator that we saw when we learned when we was studying the simple harmonic oscillator. So the displaced single harmonic oscillator ground state that we will do today using the coherent states, that's we will see that's a consequence for the things that we define today is like the displace the ground state of the single harmonic oscillator. So this type of ground state here, the wave function associated with the ground state satisfies the properties of the wave packet oscillates in the single harmonic oscillator potential without changing the shape. So that's the state with the minimum uncertainty. I mean, the minimum uncertainty related with the uncertainty principle, right? When we relate like the momentum and the position of in this case, the photon. So all the photons generated here has the same amplitude and the same phase, and has this property of the minimum uncertainty. We'll prove this probably in the next lecture, not today. Because in the next lecture, my idea is to give some properties. Today will study the basic theory behind the coherent state, and the next we'll see some consequences and apply quantum computation. And this figure here is in this book. It's part of the lecture today. I use this book here, Quantum Optics, by Scully and Zuberi. These figures in the page 47 is this book here. I have also the PDF. If people need, I can put maybe in Zoom or in the GitHub. Okay, so this is the last slide for today. So classically, electromagnetic field consists of waves with well-defined amplitude and phase. But when quantized, this is not the case because we have fluctuations associated with the amplitude and the phase of the field. We will not see details about the quantization of electromagnetic field today because this will be, we'll do this in the next topic when we study quantum electrodynamics. So we'll see with more details. Today, I will give just a brief idea how to quantize the electromagnetic field, and then define the coherent states that what we are interested for this optical photon quantum computer. So, okay, this is just a brief summary. Let's understand better using the whiteboard. If you guys have some questions, can interrupt me anytime. So, okay. Define, let's just remember a little bit about the classical electromagnetic field, in this case, the electric field. Okay. So, let's put for a field in a cavity. In a cavity, because remember we want to produce lasers with this property, with the minimum uncertainty, because we want to generate like single photons, right? So generate each photon with the properties of the coherent state. So for a field in a cavity, and this cavity has side L, the classical electric field can be expanded in terms of plane waves. Okay, and we do this like solving Maxwell equations. I'll give here only the result. Okay. So the electric field at time t, position r, can be expanded in terms of plane waves. Like k is the wave number, and we have these quantities that we'll define soon. E of k exponential t k. Plus, we'll call here complex conjugate of this, okay? So let's define this. CC here, just the complex conjugate. conjugate of this, the same thing. This EK here is just the unity polarization vector. This alpha K here is just a dimensionless amplitude for this wave. What else? This guy here, EK, is the definition. Okay. Omega K is just KPC0 over M. There is no storage bar. Okay, and V here is the volume. And epsilon 0 is the free space permittivity. Space permittivity. C0 is the speed of light, the part. Speed of light. Okay, and K here, this K here, that is a vector, so it has 3 dimensions. Let's write in a cavity, K is just when the field is like closed in a cavity, it's just, let's call this yeah. We have this I here, it's X, Y, Z, okay? Okay, so this is the electric field, classical electric field in a cavity. And the Maxwell equations, right? Maxwell equations requires that this guy K E 0. Okay, so the fields are transverse, but there are two independent polarization directions. Of EK for each. Okay, just to like review some things about the electric field. The thing is that we are really interested here is Let me change the color. Is that the radiation field is quantized by the identification. By the identification. This. I will identify the amplitudes alpha k with AK that we defined in the last lecture about the single harmonic oscillator, the destruction annihilation operator, and the alpha k conjugate with the AK dagger. So the single harmonic, the identification in the quantized field, electric field, is quantized by this identification with the single harmonic operators. And remember that they satisfies, and we saw this in the last lectures, it satisfies the commutation relation. AK, K danger. Well, to identity, yeah? We call demand here. Okay, so let's do this. So in this way, the quantized field E of RT will have this expression. The sum over K EK epsilon K. Instead of alpha, we'll have like AK. Exponential minus negative times ITI power plus the harmonic conjugate. Okay? And we see this in details when we study the quantum electrodynamic model. That's the next topic. Today, just this is enough, because using this, we will define our coherent states that the things we are really interested. So this is just to remember and to give some idea, but we'll see in details the consequence of these definitions when discussing the QAD, quantum electrodynamic model. But okay, just to comment, like we can, doing this, we can interpret this field as an infinite number or infinite set, I think is better. Infinite set of oscillators. Attached to each point in space. each point R. Okay, so this is the how we in general model fields. Like we use this like the electric field, but we could use this for the type of field like scalar fields, and the magnetic field would be something similar. So to relate this with the coherent states that we are interested. So in this case, coherent states are naturally since we will define coherent state by this, we'll do this soon. So coherent states are naturally radiated. It's the radiation, right? The electric field. Radiated from oscillators. Oscillators such as lasers. When pumped above its lasing threshold. So this is maybe the best definition for coherent states using this type of model. So, but to define formally, let's define a coherent state as the radiation emitted by classical current distribution. Such a state. By classical current distribution, so by classical, we mean that the current can be described by a vector. Vector let's call J of R and T, which is not an operator, okay? Oh, a vector. It's not an operator. So this J here is just the dipole coordinate. And the idea is consider the couple of this current to the vector potential operator. The vector potential is defined in terms of the electric field, the quantized electrical field. So let's call A, cap A. So A, that's the potential operator of R in T, is defined just the sum over K, 1 over omega K, and the terms from the electric field. So EK, epsilon, the quantized field, because this now is the operator. Okay. Instead of the amplitudes, we are defining the this is the, like the oscillator, this is the annihilation operator. And exponential minus I omega K T plus I K R plus the harmonic conjugate. But I will write here because it will be easy to see this in the future. So I will write here the other part. That's the harmonic conjugate of this. So it's just 1 omega K, EK, epsilon K, all these things are real. Here, AK dagger, and exponential. Minus Q. So you can see here these terms. This term with the sum is the electric field. Okay? Apart the omega here in the I, because this is the potential. Okay, and to couple, to make the couple here, this couple between the operator, this operator, and I'll call this equation star, because I'll use in the future. So the couple of this equation start with the current distribution will be given this way. We will define the Hamiltonian, defining the Hamiltonian that describes the interaction between the field, or in this case the potential, it's related to the field and the current. Is given. Define the Hamiltonian that describes the interaction between the field and the current. So that's the Hamiltonian. Age depends of t, because this guy here depends of t. Integral of j jr scalar with this operator here, the vector potential operator. So I'll write here this way. Notation not so good. T3R. I'll call this 3 stars. Okay, so this is the definition of the Hamiltonian. That's a classical term and a quantum term. Sometimes this is called like semi-classical field when you have like this mixture. And to describe the dynamic, we use the Schrödinger equation. We'll define the state vector. So the state vector, I will call psi of t, obeys the state vector for the system of this system obeys the Schrödinger equation. And just to remind, d dt psi is minus I h bar, the Hamiltonian operator psi. Okay, we can just some properties. The vector j RT commutes. It's a classical thing with itself at different times. But the operator A of R and T does not. So we can see this as a homework, okay? A doesn't commute with itself because of the definition, right? It depends of A in A dagger. And A and A dagger do not commute. But okay. So since we have this, the Schrödinger equation, we can solve this equation here. And we can see that psi can be written this way: exponential minus I h bar integral 0 to t bar dt h of t psi 0. Okay? And we don't know how to solve this integral because we don't know the form of j. Yeah. But it doesn't matter here, you see. So we can like simplify this and use some properties of the commutators. So let's use equations that I call star and star to simplify the integral. So, okay, so let's use these equations that we defined before, and then just write here the expression to simplify this. So 0t dt h of t. This is the, using the definition of h, this will be just let's see here. Will be just minus I h bar, the double integral, because this and the definition of h t d3r j of r and t times a r and t. Okay, so let's use, I think it's the equation 1 star that we define a. So let's use a here. And then we could use like the properties of the operators. So we'll like, I use equation 2 star here because it's the definition of h. So remember, this is the definition of h, the Hamiltonian, and the equation 1 star I'll use. So this will be just integral dt r is j here of t times, so I will use the definition of the potential. But here is minus the sum of k 1 over omega k h bar. This h bar here is this, and this I, it's better with this I here, and this h bar appears, let's see, R cancel with this, and the h bar will appear here. So just like right here, ek epsilon the operator exponential minus I omega k t plus I k r. And the other term is the sum 1 over omega k h bar ek epsilon k zaga exponential I omega k t minus I k r. Okay, just use the definition of a here and multiply by this term. Okay, so we can define here, defining a new complex time dependent amplitude alpha k. Okay, this is a new alpha k. It's not the first slide that we define. Just related with the operators, the creation and manipulation operator. So this alpha k here that we find, let's call green alpha k, is just, I will define like this term here, apart the operator, so will be something like this. Something like this. This term. Okay. So alpha k will be 1, like the integrals. One over omega k h bar k h bar ek the integral, the dt integral and the 3r plus this term here with this term here inside ek scalar, because it's the scalar product here. This is the unity vector. And the problem with the notation, right? Sometimes you use this like operator, and here using this is just a unity vector. So I'll put the arrow just to the operator on these guys, and this is the unity vector. So this is J of R and T exponential I omega K T minus I K R. So this is my new amplitude, alpha K. So I can write the exponential, the original term, like this. Using this new definition, I can write this exponential here in this way. This. So you see that the exponential, so exponential minus I h bar integral dt 0 to t prime ht. This will be just like the sum, exponential of the sum, because I define alpha k here, so this sum is outside. Let's see here. I have this sum here is outside. So this and this sum. So they are here, sum of k of minus, this minus sign, alpha k, that's all this guy here. Alpha k. In fact, alpha k star, this is the definition of alpha k star. Okay. Let's see something wrong. Yeah, because this, okay, this is alpha k. This is the definition of alpha k. This is positive, and this is negative. So this first term here The system here is negative and positive here. But alpha is defined in this way. So this first term is the alpha star, alpha conjugate. So the conjugate times AK. And the second term is the definition of alpha times this guy here, A dagger. So plus alpha K, K, A dagger. Okay? So with this definition here, the term that is associated with the term associated with the annihilation operator is the alpha conjugate, and the other term associated with a dagger is the definition of alpha. So okay, and because we have the sum of several sum of the exponential of sums, so we have something like this. Exponential of the sum is the exponential of the product. Or you can think the exponential of sum, let's say a's, this is exponential of a1 plus a2 plus a3. That's the same exponential of a1, exponential a2, exponential a3, and so on. That's the same with product. Exponential a1. So you can write this as the product k of exponential of k dagger minus alpha k. Okay. Okay. See my time here, it's almost 4. So okay. I need to be quick. Okay, so let's choose the initial state psi of 0 to be the vacuum. I'll call 0, the ground state, right? So the Schrödinger equation, the solution of the Schrödinger equation, the psi of t. So the psi of t will be just psi of t. That is this exponential. Remember, psi of t was something like this. dt psi 0. So calling psi 0 as the state 0 and using this thing that we just proved here when we use the definition of h. So we can write this guy here this way. So psi of t will be just the product of the exponentials of k E delta k minus alpha k star 0. Okay. This is my psi t. And 0 for different k's, okay? Because I have the product of k's. So this is the state of the radiation field. And this state is called coherent state. And it is denoted by. So the coherent state, I'll call alpha of t, is the product of alpha k. Where this alpha k is this guy here in the right, where alpha k is just this exponential alpha k, ak dagger, minus alpha k conjugate, ak 0 k. So this is the coherent state. But, however, we will be mostly concerned with a single mode coherent state. So in this case, because we're interested just in a single mode, so we remove the k, and we can write the coherent state alpha, this guy, just for a single mode state. Conjugate A. 0 is the ground state for the oscillator. I'll call this equation 1, because I think I put 1 here, I'll use in the future. So just to remind that this expression was obtained by defining the coherent state of the radiation field as a state of the field generated by a classically oscillating Coherent distribution. That's our J, right? Remember that the definition here, the J is inside the intervals distribution when we define the alpha. So my idea here, just to see if you, my idea here is to give some properties, to study some properties today, and we have some applications in the next. But I don't know about the time. How? First of all, you guys are here yet? Or?
Still here.
Yeah, okay. So I'll keep going, but if you guys be tired, so you can tell me that I can like split, maybe record a second part, okay? So okay, just following the same expression for alpha can be obtained by defining it as an eigenstate of the annihilation operator. With eigenvalue I'll call alpha. So to see this, note that. So if I have the A operator applied to this equation 1 here, so A applied to alpha, it is A applied to all this guy here. So to the exponential of alpha A dagger minus A 0. So, but this is exponential of operators. So we need to see how it acts here. So this is exponential of A times exponential of A dagger exponential minus alpha A 0. So we must first see how this guy here acts on the vacuum state, on the ground state. So we will see here exponential minus alpha conjugate A applied to 0. We can expand these exponentials. So 1 alpha conjugate A minus alpha conjugate square over 2 K squared plus the other terms applied to 0. So we can see here, this guy is just 0, it's 1, like the identity operator. It will be just 0. And A applied to 0 is 0, remember, the annihilation operator. So you have nothing This is the ground state. So below the ground state, you have nothing. So the annihilation operator, when applied to this guy, is 0. And a square will also be 0, and a to the cube will be 0. So in the end, the only term difference of 0 will be this. So this guy here, this first part here, this is give me just the vacuum state. It doesn't change. Nothing. And so this other term here, exponential of alpha a dagger applied to 0. I'll do the same thing. So expand this. This is plus because the sign. So alpha a dagger plus alpha square over 2 a dagger square plus the other terms applied to 0. So here the thing will be different, will be 0, the first term. The second, you have alpha, a dagger applied to 0 will be just the state 1, plus alpha square over 2. A dagger square applied to 0. We saw the general expression in the last lecture. This will be, the second will be just the square root of 2 times 2, because we applied 2 times, right, to the vacuum state, and so on. In general, we saw this in the last lecture. This will be something like this: alpha n over n. So okay, so this is this part, but remember that we still need this thing here. Okay, we saw that this do nothing to the vacuum state, and this other part, when applied to the vacuum state, will give this expression. But now we need to apply the a to this expression. So a applied to this expression here, this will have 0 plus alpha 1 plus alpha square 2 square root of 2 in the other terms. So this will give me a, because this is the annihilation operator applied to 0 is 0, and this will have alpha, this alpha here, but 1 with the annihilation operator, this will be the state 0, and so on for the other case. This will be alpha square 1, and so on. So in the end, we'll find that this guy here will give me, like, I'll put alpha in evidence. This is 0 plus alpha 1 plus the other terms. But this state here is just my state alpha, right? This is just my state alpha. Because my state alpha is exactly this one here, right? 0 plus alpha 1, and the other term alpha 2 square over 2, and so on. And just check here. Alpha is this guy here. And we saw that this first part applied to vacuum has nothing. The second part is the same, this here, which is the same here. Okay. So this is alpha, alpha. So returning to the beginning, A applied to the state alpha is just this here, alpha, alpha. Okay. And to study, so this is an important property. The other is to study the coherent states more carefully. Introduce a new operator that I'll call D of alpha, which is thus that exponential is A dagger minus A. So my state alpha, which is this guy here times this guy he applied to the vacuum state, will be just the D alpha to the vacuum. And we'll see now that the operator D of alpha displays the amplitude A by the complex number in the complex number alpha. What I'm saying that D applied to alpha A D alpha, this will give me A plus a displacement alpha. So to prove this, let's imagine that alpha is decomposed into infinitesimal quantities. I'll call delta alpha, okay? So in first order of delta alpha, we can use this definition here of D and apply to this thing, this guy here. So D delta alpha applied to A, D delta alpha. This is just exponential alpha conjugate A minus delta alpha A applied to A exponential delta alpha A dagger minus delta alpha conjugate A. So we can expand this up first order. Up to first order in delta alpha we obtain. So make this expansion very quick here. This is 1 plus A delta alpha minus A delta alpha plus the other terms times A, and expanding this A dagger delta alpha minus A delta alpha. So we can see in first order in delta alpha that this could be right A plus A multiplied by A dagger delta alpha minus A delta alpha conjugate plus A delta alpha conjugate minus A delta alpha. Yeah, I forgot something here. There is a dagger somewhere here. A dagger delta alpha yeah, I think I'm missing a dagger somewhere here. But okay, you guys can check this is really right, okay? Just a step here. Because it seems this guy, well, maybe he's right this way. You guys can check. It's easy. It's just to multiply this. I'm giving here. We can. The thing is, we can simplify this by writing this way. A dagger delta alpha minus A delta alpha dagger. Okay, you can write this in terms of the commutator of A with the expression with D, right? The expansion. Okay, and because of that, we can like write this as A. So delta alpha is a number, so we could use that properties. A dagger is the commutator of this with the first minus delta alpha A, the commutator with A. So this we saw last is 0, and this here is 1. So this will give me A, so it's 1 times delta alpha. And because alpha is the sum of delta alpha is a small displacement, so the total alpha is the sum of this small displacement. The total displacement operator, d of alpha will be the product of the d of alpha, right? Because the d of alpha is, again, is that properties of the exponential. So d of alpha is just the exponential of a, sorry, this is delta alpha, a dagger delta alpha minus a delta alpha conjugate times exponential a dagger delta alpha minus a delta alpha conjugate in the other terms. So in the end, this will be the sum. Exponential of a dagger, the sum of the difference, minus a, the sum of delta alpha conjugate. And we can apply, so we would apply the infinitesimal steps delta alpha as often as we need to show that. So to show that d dagger alpha will be applied to a, alpha will be just a plus the sum of delta alpha. So if you apply like many times, but the sum of the small displacement is just the alpha, the total alpha. Okay. So we'll call this 3 stars because we use. Yeah. Okay, and if we apply, so this guy here, this because of this property, is important. So because the effect of to displace, it can be called like the displacement operator. But let's see, if we apply a negative displacement to alpha, so if I have a and apply d minus alpha to alpha, I can use here, so apply a to the displacement in the coherent states, but a negative displacement, and then apply the annihilation operator. So I can use the fact that d dagger is equal to the identity operator. So d of minus alpha, d dagger of minus alpha, apply. I can write this, where we can check that is easy to see. that this is the identity, right? So let this is homework. So since we have this property, d dagger out of alpha a d alpha, this guy here, d dagger minus alpha a d minus alpha, this will, using this here, this will be giving just a. So instead of plus, instead to displace to the positive side, I'll displace to the negative side because the displacement is negative. This is minus alpha. So a d minus alpha alpha. So I use this here. This property is here. Okay. So this guy here is this right here. So this will give me just the d of minus alpha of a minus alpha alpha. But a applied to alpha, we saw it's just the alpha state. But a alpha is alpha alpha. So this will be 0, right? A d to the minus alpha alpha will, this guy here will be 0 because of that. So this is d minus alpha alpha minus alpha alpha, which is 0. So a applied to the aniquilation operator applied to this state here means that I have 0 results. So this implies that d of minus alpha alpha is the vacuum state. Because a applied to the vacuum is 0, the aniquilation operator. So consequently, a coherent state is the displaced vacuum. In other words, alpha d of alpha is the vacuum spacer. Okay. So just to finish for today, let's just see another important thing. That's the relation. Let's change the color. Now, let's study some particle aspects of the coherent state. For this purpose, we seek the number representation of the alpha 0, which is the state alpha, right? So let's use the what's called Campbell Baker Hausdorff formula to represent D in a different way, in different form. Okay, so this Campbell-Baker Hausdorff formula we can write in a spatial case, because the general expression, let's see, just because. So this, I'll call this CBH, okay? So the CBH formula, in general, it's give the exponential of operators, A and B are operators, would be writing in this way. A plus B plus the commutator of AB over 2 plus 12. So the commutators of the commutators, so is a complicated expression, plus the commutator of the commutators and the other terms, okay? This goes like never change. So this formula is important in the theory of V groups. So the mathematicians knows, I think, knows better than me this. But for quantum mechanics, in general, the importance is these first two terms, because in general, these things here, the A, B do not commute, so we have these two terms here. But in general, the commutation, like A, B, if A, B do not commute, but they commute with one of them, the commutation of A, B commute with B, in general, in quantum mechanics, right? So that's why the importance, for instance, like if we use A, like what we define A, alpha A dagger, and B minus alpha conjugate A, and we use this formula, the general expression for this formula. So the exponential of A dagger, exponential of minus alpha conjugate A, this will give me, just so using this exponential of alpha A dagger minus alpha conjugate A plus I'll just write here, so it will be alpha over 2, the commutator of A dagger A, and plus this other term, 1 over 12, and the commutator of A dagger A, commutation with A dagger, plus A. Now here's A dagger commutator of A dagger A, and other terms. But so this commutation here we proved the last lecture. This is -1. So this guy do not commute. So I can write this using this thing here, this property here. But because this is -1, so 1 commute, A commute with -1. So this term will be 0. And the same here. This is -1. A dagger commute with -1. And this will be 0. And this will be used to the other term. So in general, in quantum mechanics, the importance to this formula is using the until this term here. This other in general is 0. So using this here, we can write the exponential of alpha A dagger minus alpha conjugate A. We will have just like this first term, alpha A dagger, exponential minus alpha conjugate A. And this term here, that is just a number, exponential of minus -1 over 2 alpha conjugate. I think this here is minus, not plus. This is minus because my notation is my plus here. Alpha conjugate. Okay. So I could write this because this is just a number, exponential of a number. So this is exponential. Now it's right. Always right. This is plus. Sorry, this is plus, and this is minus. So this is exponential of minus alpha square, exponential alpha A dagger, exponential minus alpha. So I can write this in this way. It's the same symbol. But this form of writing is better to study the number state. So we already know, just to remember, we already know that this guy here applied to vacuum because the annihilation operator do nothing to the vacuum state. It's the same. We saw this in the beginning. And this other exponential I A dagger applied to the vacuum gives just this alpha n over n factorial. So this is the same. This is the displacement operator, right? And I can write it this way or this way. It's similar. This is the displacement operator. So the alpha is the displacement operator applied to the vacuum. And because of that, so if I use this term here applied to the vacuum, this will give me just this number, exponential, minus 1 over, let me write. This will be just this number here, minus 1 over square. This term applied to the vacuum, that is do nothing, and this other term applied to the vacuum, that do this. So time for the sum, and it's 0 to infinity. Alpha n over n factorial. Okay, and this is just the equation 716 from Nielsen-Schwenk book. So the Nielsen-Schwenk book just give you this equation, but our idea here is to understand the details, right? How they came for this equation, this Nielsen. Sure. So, okay, this is the relation for the coherent state with the number state of the harmonic oscillator that we saw. So we will use this to do computation in the other opportunity. So my idea, I don't know, I could like start from this in the next lecture, from this equation, and do the things that the Nielsen-Schwenk was doing. Or maybe we could start a little bit, we could study a little bit more some properties of coherent states, and then do the thing. So my idea is the second. I think it's better we understand a little bit more some properties of coherent states before doing some applied to computation, because so far it's just like quantum optics, and was a little bit, maybe a little bit fast, but I don't know what you guys mean. For today, I think it's enough. It's almost 2 hours. So, yeah. So, thanks for you guys that follow. It's almost 2 hours of lecture. So,
Thank you.
any questions? I mean, this is the Nielsen-Schwenk starts from that equation, but I try to give some from what's the origin of this equation. He just gives some few words and some couple of sentences, and okay, let's do computation. But I mean, I think the idea here is to understand the details. So even like doing this is a little bit fast, but I mean, yeah. So the idea is the next lecture show some properties, and then we go to the Nielsen-Schwenk and start doing computation. So.
That's a lot to digest. Thank you.
Yeah. It's a lot of. As I told you before, like the Nielsen-Schwenk book is very dense book. Each page has a lot of information. So if you want to understand really understand the things, we need to see a lot of things. So okay, so I think I'll stop recording because I think it's already too long. And if you guys have questions, you can